Welcome to the 2020 Informs OR and Analytics Student Team Competition. I'm delighted to introduce the finalist presentation by the team from Bilkent University, Turkey.
Good afternoon, everyone. We are the team from Bilkent University, and here is our team members. From the most left, Toprak, Naz, Berk, Zeynep, me, Buse, Aslı, and Buse. And we are going to present you our project for the competition. Here you can see today's agenda. First, I will briefly mention about the problem. We are given a network design and facility operations problem that takes place in a jelly bean manufacturing company. And the first part of the problem is to reallocate the raw materials, and the second part is to determine the internal work order for each facility. And for the methodology we used, first the objectives of the problem are considered, that are the minimization of the total cost and maximization of the fulfilled demands. And to achieve these objectives, internal work orders for each facility should be determined. And here you can see our proposed approach consisting of two stages of optimization model and the simulation model. Stage 1, determining the transfer and production amounts. Stage 2, scheduling work orders. And the final simulation model. And the outputs of the optimization models are the input to the simulation model. Also, the first stage gives input to the second stage. And the aims of the first stage are to determine the transfer amounts of jelly beans between facilities and the internal work orders given to each facility, while the second stage aims to obtain the sequence of these internal work orders. And finally, the aims of the simulation model are simulating the process of each facility by including all the constraints and assumptions and evaluating the results of the optimization model. And the data is detailedly analyzed to be used in these models. We are provided with the historical data of processing rates of flavoring and packaging machines. And the rates are not deterministic but random. Therefore, a distribution is fitted to represent randomness in each rate, either theoretical distributions or empirical discrete distribution. And we see that most of them are coming from the normal distribution. And here you can see an example of a normally distributed packaging rate. And the distribution having long tails are truncated so that we don't have too large or negative values for the processing rates. And in the optimization models, means of the processing rates are used, whereas in the simulation model, random processing rates from the fitted distributions are used. Now I will describe the two stages of our approach. Stage 1, determining transfer and production amounts. The objective of this stage is to minimize the total cost. And in this model, demand fulfillment is written as a constraint instead of writing it as a part of the objective. Because it is assumed that the demand is fully satisfied after checking and verifying that the model gives a feasible solution and the demand is forced to be completely satisfied. And the same check is done for the excess raw material. So we conclude that total capacity of all facilities is sufficient to process all the raw material with the mean processing rates. And the flavor assignments to the excess raw materials are made by considering the percentage of each flavor over the total demand of each color size combination. Because we want to have a meaningful stock of jelly beans by considering the possibility to sell them in the future. And here you can see the sets which represent the facilities, colors, sizes, and so on. And the parameters here are the ones that are already given in the problem statement. Only the most below one, eta, is calculated to assign the flavors to the excess raw materials. And it is the ratio of demanded jelly beans of each flavor over the total demand of each color size combination. The decision variables. T is the transfer amounts between facilities. P is the production amount of each type of jelly beans. I is the inventory levels after the transfer. X is the number of aramide drams used for each color. And finally, E is the amount of excess jelly beans. And the objective is to minimize the total cost, consisting of three parts. First part for the transportation cost, then the production cost of demand, and finally production cost of excess raw material. Inventory constraints. The first constraint shows the inventory balance and the other two show the usage of RMI drums. Capacity constraints. The first constraint is the classifier split and the other three are the time constraints for classifier, flavoring, and packaging operations respectively. And finally, transportation, demand satisfaction, and the domain constraints. In this part, first constraint is not to exceed the track capacities, and the second is the demand satisfaction constraint. Now, stage 2, scheduling work orders. As I mentioned before, the first stage gives the internal work orders given to each facility, but it doesn't give the schedule of them. However, the schedule of the work orders is also significant since the sequence changes the total flow time of the production. And all the process can be actually completed in the 6-month production period with the given data and the mean processing rates. However, to find a production plan that maximizes the satisfied demand in case of a different scenario where the demand cannot be fully satisfied, it is decided to schedule these internal work orders so that the amount of satisfied demand is maximized by decreasing the total flow time. And the objective here is to minimize the weighted sum of total cost and amount of unsatisfied demand. And the minimization of the unsatisfied demand is prioritized by giving a larger weight to this part of the objective. The parameters of this model, I hat is the optimal inventory level obtained from stage 1. W is the weight to prioritize the minimization of the unsatisfied demand. And beta is the key point in this model to find the sequence, and it is a multiplier to represent what percentage of the capacity is used for each machinery. And P hat is the optimal amount of jelly beans of each type produced at each facility. And this is also taken from stage 1. The decision variables. P is the production amount for each type of jelly beans at each facility. And UD is the amount of unsatisfied demand for each type of jelly beans. And the first part of the objective represents the production cost, and the second part is the amount of unsatisfied demand. The capacity constraints. The first constraint is the classifier split, and the remaining are the time limitation for each process with the beta multiplier to decrease their capacities. And finally, demand satisfaction and the domain constraints. Demand fulfillment is not a necessity in this model because we observe how much and from which type of shell beans the system gives up producing as we decrease the capacity. Now, Berk will continue.
In this model, we use a new parameter called beta, as Buse mentioned, that represents the capacity usage of facilities. Also, two new measures are defined for computation purposes. Alpha IK is the ratio of total production amount of each color in each facility divided by the optimal production amount of each color in each facility. And alpha IKF is calculated using the same reasoning, but it is for each color, flavor, and facility. In order to find the schedule, initially the value of beta is decreased. The aim is to determine which product types does the model give up to fulfill in each facility when the capacity is decreased. And we observe that when the value of beta is less than or equal to 0.5, the model cannot fulfill all the demand anymore, and unsatisfied demand variable starts to take positive values. So, by decreasing the value of beta from 0.5 to 0.1 by small decrements, the values of alpha variables are observed and saved. Then the average of these alpha variables are calculated. These average values are sorted from largest to smallest, which gives us the schedule. Because if the average value of alpha for each facility and each color is smaller, then this means that in that facility, when the production capacity is decreased, model does not prefer to produce that type in that facility as much as the types with larger alpha variables. The same reasoning is used for both alphas. Now I will talk about our simulation model. After we obtained the schedule of the work orders or facilities, as a final step, we built our simulation model. First aim of our simulation model is to simulate the process of each facility by including all the constraints, assumptions, and especially using the random processing rates with their fitted distributions respectively. And second aim is to evaluate the results of the optimization model. Here you can see an example of our input to the simulation model. First 5 variables come from our optimization models, and the rest of them come from our analysis on data. Now we are moving to our analytical solutions and results. After all these stages, our main results are listed here. Some of them come from our optimization models, and some of them come from our simulation models. These are the transfer amounts and cost of transportation that come from our first stage optimization model. As you can see, all the transferred amounts are towards the Oman. These results inspired us to come up with our first recommendation that will be explained later, that has to do with the reallocation of trucks. These are the facility-based production results: total production amounts, total number of days to complete production, and total production costs. These costs and amounts come from our optimization models, and total completion times comes from our simulation model. As you know, 6 months production period is equal to 182 days, and as you can see, on the average, we are able to process all the raw materials within the time limit. Here are the utilization percentages of machines and bottlenecks. As you can see, the biggest ratio for each facility indicates the bottleneck operation for that facility, and these operations are shown in red. And at last, here is our overall results regarding total cost. As you can see, all the production and transportation costs are summed up to be close to $38 million. Finally, after analyzing the outcomes of our models, we developed some recommendations for the jelly bean manufacturing. Our first recommendation implies that the reallocation of trucks that are already placed in each facility will be more efficient in terms of costs. Since trucks in some facilities was not used to distribute raw materials, we can shift these trucks to other facilities. Specifically, having 2 trucks in Columbus, 3 trucks in Springfield, and none in the others reduces the total cost by approximately $47,000. Second one is about initial raw material distribution to facilities. In order to see what would happen when the initial inventory levels are different, we run the optimization model with the end inventory levels after transportation is finished as initial inventory levels. We did this iteratively for 7 times, and it decreased the total cost by nearly $470,000. By doing this process iteratively until the cost stops changing, the optimal initial inventory levels can be found so that the raw materials can be distributed to facilities optimally and the total cost can be decreased more. Our third and last recommendation considers the facility at Green Bay. In case of a breakdown, Green Bay can be allocated as a backup facility since the work order assigned to Green Bay is the least amount and lasts the shortest. Here, as you can see in the table. That was all our recommendations. Thank you for listening. Special thanks to our advisor Özlem Çavuş. And if you have any questions, please do not hesitate to ask.
Excellent. Good for you. Thank you very much to the team from Bilkent, and John Burge. Professor Burge will coordinate the judges and asking some questions. And you probably keep sharing your screen, Turan, in case you want to end up going back to look at some of the slides.
Yeah, okay.
As the questions are asked.
Right. Thank you, Busa and Berk, for your presentation. We have a question from David Bergman.
Yes, thanks, John. Excellent work, team. It's obvious that you put a lot of work into this, and I think it really showed in the presentation. I really like that you closed with concrete recommendations. I think that was really excellent. But I do have a question about the utilization rates. So the utilization rates for you were in like the very, very high 90s, right? Have you thought about maybe running the simulation model, enforcing that you can only use 95% of capacity, for example, and seeing how that affects total costs and orders that have not been able to be fulfilled? Were you able to hear my question?
Sorry, can you repeat again?
Sure. So if you look at this slide, you have utilization rates of near 100%, right?
Yes.
Have you thought about doing a bit of a sensitivity analysis on this and saying, what if we only allow ourselves to use each one of these processes up to 95% or so? And what would be the total effect on total costs and total number of unfilled orders, just to get a more understanding of what could happen, right? Because, you know, these are very, very high. Just a question for you, if you did any experiments there.
Maybe I can answer. In this facility, if we use a 95% top utilization level, it will probably increase the total cost, since it will shift some of the demand to another facility that has a higher cost. But these utilizations are not representing the real utilizations of the 6 months. This utilization only represents the total flow of time of that facility. For instance, for Green Bay, it is like 64 days or something like that. So it is the 99.65% packaging operation for only 64 days. So actually in 6 months, it is not really at 99.6% utilization.
Okay, thank you.
Okay, thank you. We have a question from Shrikant.
Hi, everyone. Good evening. A great presentation. A quick question on the utilization. How did you define utilization?
Actually, the simulation model automatically gives the utilizations in the report.
So that means, for instance, if the total flow time of that facility is 60 days, for instance, if the utilization for a machinery is 99%, it is probably like 89 or something like that, 89 days or something like that for that machine.
Sure. So, for example, if you had an operation that is blocked by the downstream operations, so would you consider that as part of utilization, or would it be idle time?
Can you repeat the question again? At least I
Sure.
couldn't get it.
Sure. So, for example, if your packaging line is running busy and then your bins in front of packaging line are all filled up, so now your packaging operation cannot run, right? The pre-finish operation cannot run. At that time, do you consider that pre-finish equipment to be idle, or would you consider the pre-finish equipment to be busy, though it's not working?
I think it is counted as idle time for that machine if the machine is not processing.
Okay. Thank you.
Okay. Thank you. We have a question from Mark Mekaten.
Hi. I'd like to echo what everyone else has said. You gave a great presentation. One of the most fascinating things in your presentation, at least to me, was the use of beta and trying to decrease the production rates to select priorities of work orders. But I'm still not quite getting the intuition why decreasing the production rates to see which work orders would kind of fall out is really the optimal way of sequencing. And I'm kind of hoping that you could spend a minute or two more to explain that.
Actually, our aim is to choose the product types with higher processing rates with lower costs if we cannot fulfill all the demand by this way. So our schedule gives the priority to product types with higher processing rates to achieve in a less time maximizing the fulfilled demand. In a less time producing much more demand. Is that the answer you are looking for?
So you're basically, just to repeat what you just said, you're prioritizing by, in some sense, efficiency, as opposed to looking at more structural parts of the manufacturing. You're saying do the most efficient ones first, and then whatever time you've got left, do the
Yes.
least ones. Okay, thank you.
Yes. Thank you.